In this section of the course, which really begins Module 2, we're going to discuss biopotentials and the origin and the measurement of biopotentials in the body. So this is primarily dealing with biomedical instrumentation that measures voltages and or currents that are emitted by different parts, usually parts of the central nervous system or the peripheral nervous system. So um, we'll talk initially about where biopotentials come from, and then in the latter part of the module, we'll talk about how we make contact electrically through the skin to measure biopotentials, and then finally a little bit about the instrumentation associated with acquiring and processing these signals. So for the first part of the material that is in Chapter 4, which is the origin of biopotentials, I pulled a great deal of the lecture from a reference on Wikipedia, two references actually. This is the first one. You can find it at the link shown here. This discusses a membrane potential. So basically, what is a membrane potential? It's also known as a transmembrane potential or the membrane voltage. It's basically the difference in electric potential between the interior and the exterior of a biological cell. So with respect to the exterior of the cell, typical values of the membrane potential range from minus 40 to minus 80 millivolts. So this is a figure cited as shown above that illustrates a little bit of what's going on both extracellular and intracellular. So extracellular means outside of the cell, intracellular means inside of the cell. And the main thing that happens is, and here's another range of membrane potential voltages, this one, and this should be negative, this one going from negative 40 millivolts to negative 70 millivolts. So basically what happens here is that certain ions are present inside the cell at a different concentration than they are outside of the cell. Potassium is one of these. It has a high concentration in the cell and a low concentration out of the cell, whereas sodium and chlorine tend to have higher concentrations outside of the cell and lower concentrations inside of the cell. So basically what happens is the the ions that are present in a high amount, like potassium inside the cell, they basically will diffuse through the cell membrane. And as they diffuse through the cell membrane, they create a voltage. So if the membrane, for example, is selectively permeable to potassium, then the potassium ions will diffuse through this concentration gradient and go outside of the cell. And what happens then is you have uncompensated negative ions that remain inside of the cell. This gives rise to cell potential due to charge separation. And because of this cell potential, then there's a little electric field created across the cell membrane that acts in the opposite direction on these positive potassium ions. So diffusion forces are driving the potassium ions out of the membrane, while electric field forces are trying to push them back into the membrane. Ultimately, what happens is those two forces reach an equilibrium, and you have just what is known as a resting state potential in the cell. So electric signals within biological organisms are primarily driven by ions, and the most important positive ions for the action potentials are sodium and potassium. Both of these are what we call monovalent cations. They carry a single positive charge. We can also get action potentials that involve calcium, which is a divalent cation or has two positive charges. And chlorine is an ion that plays a role in some types of algae, but generally does not play a role in humans and animals. So what do we mean when we say action potential? The action potential is what happens when electrochemical forces create a situation where the cell potential changes with respect to time. Now, this change can happen slowly, or it can happen due to diffusion processes, or it can happen rapidly when the voltage exceeds some sort of threshold. So here is a little bit of a better figure about what happens just in general when we have a semi-permeable membrane. In this example, we have two solutions, solution A and solution B. We have a porous boundary or a porous barrier in between them. And basically, because the barrier is porous, eventually solution A, the elements from solution A, will diffuse through the boundary into solution B and vice versa until we get equal solutions on either side of the boundary. Now this mixing occurs due to the difference in their concentration. The high concentration diffuses out toward the region with low concentration. So in the cell, the permeability of the membrane is greater for potassium than for sodium, except in certain cases, which means one ion will diffuse and the other does not. So you can see this process of diffusion through the semi-permeable membrane through the figure here. Now, what occurs that's actually helping with the diffusion? There are a couple of physical mechanisms and different ways that this can happen. One way, so here would be the space outside of the cell, here would be the space inside of the cell. One is that we have what's referred to as a protein channel, which is just a channel that opens and allows things to migrate into the cell or out of the cell. We also have what are known as carrier proteins. These are proteins that have a special shape that accommodate the movement of ions either from outside to inside or inside to outside of the cell. So this is known as facilitated diffusion, meaning that there are ways that this process of diffusion can be assisted in the cell membrane. So the reversal potential or equilibrium potential of an ion is the value of the transmembrane voltage at which the diffusion and electrical forces counterbalance. So there's not going to be a net ion flow across the membrane. This means that the transmembrane voltage, so the voltage, the potential difference between the outside and inside of the cell membrane, exactly opposes the force of the ion diffusion, so that the net current across the membrane is zero and does not change. Now this is important because it gives the voltage that acts on channels that are permeable to that ion. In other words, it gives the voltage that the ion concentration gradient generates when it acts like a battery. So the equilibrium potential of a particular ion is usually designated by this notation E subscript ion. The equilibrium potential for any ion can be calculated using an equation known as the Nernst equation. So here is an example of the Nernst equation, where in this case we're looking at potassium. So the equilibrium potential of potassium measured in volts is RT over ZF, where R is the universal gas constant, T is the absolute temperature, Z is the valence, I believe that's denoted by N in your textbook, F is the Faraday constant. Then potassium ion concentration with the subscript 0 is that is outside of the cell, and potassium ion concentration with the subscript I is that is inside of the cell. So the Nernst equation allows us to calculate the equilibrium potential for the different types of ions. So here's just an example from your textbook showing the same kind of thing. You'll notice they use N instead of Z, filling in some numbers and then giving some typical values for different types of intracellular and extracellular concentrations. Now the net voltage across the membrane is the function of all of these cell concentrations outside to inside. Notice that chlorine is inside to outside. That's because it's a negative ion, and that then allows us to calculate the net potential. So as you might suspect, we like to model cells using an electric circuit. This is an example of an electric circuit model of a cell. Basically, the electric circuit is shown below. Notice that each ion creates a potential. This is modeled with a DC battery. This is because the separation of charge across the cellular membrane acts like a battery, storing energy. These G's here are conductances. and basically they allow leakage currents to flow. Um, C, the capacitance, is basically the membrane capacitance. So the membrane has some appearance that looks like a capacitor. This is sometimes neglected in the model. So primarily for each type of ion, it's modeled with a conductance in series with a voltage source. This can also be modeled as a resistor, obviously. Resistance and conductance are just the inverses of each other. So that's the electrical model for the cell, the equivalent circuit model for the cell. Now, what happens when we have what is referred to as an action potential? So in an action potential, basically, this is one that models one. This is governed by what is known as the Hodgkins-Huxley phenomenon. Um, there are a set of differential equations that model a membrane potential. In an action potential, there is a threshold that when exceeded the cell, we would say it fires. In other words, you get this potential that gives you a peak and then relaxes, sometimes even reversing, and then coming back to zero. So in this case, these are changes in the conduction of the membrane potential and the membrane conductance for sodium and potassium during an action potential. So you can see that as the cell fires, you get this conductance change as a function of time. This process usually occurs over the time of about a millisecond. So in this lecture, in this part of the lecture, I have summarized portions of what are in the readings. It is extremely important that you read the readings thoroughly because not everything that you need to know has been contained in this lecture. There's quite a bit of information in there, and it's just a good overview of what happens in a cell and how we can describe that electrically. Now, this is important because when we look at biopotentials, we're going to be looking, at least in this class, at some specific types of cells. So if you think about what kinds of potentials are measured in the body, kinds of potentials measured in the body tend to be those generated by nerve cells. So if you've ever had a nerve study, or an EMG, basically you're looking at a signature of nerve fibers and muscle fibers. You also have cells that are in the brain, usually neurons, that are firing and communicating, and those generate an electromagnetic signal that can be picked up by the EEG. And then finally, if you've ever had an EKG and had someone look at your heartbeat signature, those would be cells that are generated within the heart. So all of those are biopotentials that are generated as a result of these cells having potentials and action potentials, and often operating many thousands of them, tens of thousands of them in concert so that we get a bigger voltage that's actually measurable. Now, if in general these cells, particularly for the EEG and the EMG, they are long fiber type cells. So neurons can be very long. So they're modeled just slightly differently. First of all, the primary contributors are sodium and potassium. And then there is an additional conductance that's just there to represent additional um, elements, usually chlorine. You also have the battery type action of the membrane potential that looks like a DC source, and then the membrane capacitance. Now notice the difference here is this is modeled, see this delta Z. So basically we're talking resistances or conductances, depending on your model, as a function per unit length. So because these are long and signals are actually going to travel down the length of this cell, you model the cell wall, the cell membrane, in a per unit length manner. So that's where these delta Z's are coming from. So you have the cell membrane represented here. You then have the internal medium and the external medium. A current can flow, meaning a voltage can travel or propagate along the length of this cell. So you have some potential on the outside of the cell at point Z, and then you have a potential at Z plus delta C on the outside. You have the same thing on the inside. And so typically um, you have signals that can travel along this in much the same way. If you've had an electromagnetic fields course, you might recognize that this looks quite a bit like a transmission line. The only difference being that you have these sources here representing the potentials across the cell wall. So the transmembrane potential is basically given by the potential difference between the interior and exterior um, voltage across the membrane. Um, and obviously the cell membrane will have a resistance per unit length, and that can be different for the interior and exterior of the membrane. There's a current per unit length and then a voltage across the delta Z difference. So that would be the model and how it would change if you begin to model some of these cylindrical cells. Primarily what we model here is what is referred to as an unmyelinated nerve fiber or a skeletal muscle fiber. So one of the things that is unique about nerves is that they have what we refer to as a myelin sheath. So here is an example of two different types of cells or fiber cells. So this would be an unmyelinated fiber, and you can see that along the length of this fiber there is a potential that is propagating down the length. So you have a resting membrane, and then you have this active region. So this is where an action potential has occurred, and that action potential is then going to travel along the length of this fibrous cell. Um, and so you have then just this sort of continuous distribution that then travels. Behind the action potential is a membrane that has basically recovered and repolarized. So this is in many ways very much like a transmission line model. Now, most nerve cells contain what is referred to as a myelin sheath. And this myelin sheath is not continuous, it has nodes. And so, because of that, the way the signals travel along nerve cells is somewhat different than the way they travel along other cells that do not have this myelin sheath. Um, so, the myelin actually electrically looks like a little bit of a load. It affects what we might draw an analogy to impedance. It affects the impedance of this nerve cell transmission line model. So a lot of disorders like MS and some other similar disorders are basically disorders that affect the myelin sheath. And so what can happen then if you have such neurological diseases is that this transmission line impedance changes, and as this myelin sheath becomes damaged, you'll have sections and certain nerve fibers that will have a different impedance. So if you're trying to propagate signals down a bundle, you may have parts of the bundle where the myelin is damaged, where the signal either slows or speeds up, and then other parts of the bundle where the myelin is not damaged, where it travels at a normal speed. And so the result of this is that the signal becomes desynchronized. And this can result in things like tremors or slowed response, or things like if you're trying to, for example, make your hand grasp, then it can slow down or weaken because you don't have all of the fibers acting in concert with each other. So the cell model changes as you go toward looking at different specifics, and those different specifics just depend on what you're actually looking at. Inside the brain, we have yet another model. In this class, we will not have the time to go in depth into the model of the muscle compared to the model of neuronal cells in the brain compared to the model of pyramidal cells in the heart. So that would be well beyond the scope of one simple biomedical instrumentation course. But it is important to understand that these are the electrical processes that go on at the cellular level in the body that we're trying to measure.